Hi, we're going to start into chapter 7, and I'm pretty sure it'll take 2 recordings because it's pretty long. It's 120 slides, so I will just get started with sharing my screen. Okay, so now we're going to talk about stoichiometry, which is a big word, but not really a very complex idea. It's a study of the relationship between number of reactants and number of products in any chemical reaction. So we'll go into lots of detail on this. So we're going to learn how to write and balance chemical equations. We're going to learn how to classify some types of chemical reactions. So we're going to learn about acid-base reactions, redox reactions, and precipitation reactions. We're going to learn about what it means to talk about the reaction stoichiometry. So I gave you a little idea, but we'll go into great detail. We'll learn how to measure what the yield will be in a chemical reaction. And then we'll also learn how to do some measurements based on measuring reactants or products in order to relate them to each other. So this is just a picture that reminds us that there is chemistry everywhere. And if you have a solid mixture, you need to make sure that the reactants are present in stoichiometrically equivalent amounts. So that means if it takes 2 of one product or one reactant and 1 of the other, that you've mixed them in a 2-to-1 ratio. So in order for all of the reaction to take place and not to have a bunch of excess reactant. So if we want to learn about writing and balancing chemical equations, we're going to derive chemical equations from narratives. So if you're given a reaction, for example, methane reacts with oxygen to form carbon dioxide and water, you'd want to be able to take those words and translate them into a chemical equation that would describe that reaction. So we'll learn how to do that. So we'll write and balance chemical equations in molecular, ionic, and net ionic forms. So it sounds like we have a lot to learn because we haven't really talked about those ideas yet. So in preceding chapters, we've been introduced to the use of element symbols to represent atoms, molecules, and compounds. And so a balanced chemical equation uses that symbolism to represent both the identities and the relative quantities of substance undergoing a chemical or physical change. So when we write a balanced chemical equation, we're going to have to make sure that we have the correct identities. So if it's for example, methane plus oxygen forms carbon dioxide and water. You could also have a reaction where methane plus oxygen forms carbon monoxide and water. So we have to have the right identities. And then we have to also understand how much of each of those has to be present for the reaction to take place. So this is a picture. Oh, surprisingly, they're using the example that I just used. So methane plus oxygen. Remember that oxygen is a diatomic molecule when you find it alone. So it's, in this case, O2. And the product we're forming is carbon dioxide. So that's CO2 and water. And so when we balance this reaction, what we want to do is to make sure that we have equal number of carbon, hydrogen, and oxygen on each side of the equation. And that's a result of the fact that when you're talking about a chemical reaction, all you're changing is how the outer electrons of atoms are interacting with each other. So for example, on this reactant side, the left-hand side, carbon and hydrogen are interacting with their valence electrons, whereas on the product side, carbon and oxygen are interacting with their outer electrons. So it's simply a change in how electrons are interacting, but you're not changing the number of any individual element. When we, in the final week of the class, talk about nuclear reactions, we'll see that, for example, uranium can become thorium, and that's because the nucleus is actually changing in those processes. But we won't talk at all about that for the first 3 weeks. We'll be talking purely about chemical reactions. So when you write a chemical equation, these are the elements you have to take into account. So the substances undergoing a reaction are called reactants, and their formulas are on the left-hand side. So it's the methane and the oxygen are reactants. They're mixing together to change. And then the substances that are generated are called the products, and they're on the right-hand side. So our products are carbon dioxide and water. So they're on the right-hand side. Plus signs separate individual reactant and product formulas, and an arrow separates the reactant and the product sides of the equation. So we have methane plus oxygen, they're adding together, and the arrow shows that they are changing into new species. They're changing into carbon dioxide plus water. The relative numbers of reactants and products are represented by coefficients, and they're placed right to the left of the formula. A coefficient of 1 is typically omitted. So this tells you that in order to have the right number of carbon and hydrogen, if you have 1 methane, so 1 is implied on the left-hand side, it has 4 hydrogens in it. And so on the product side, you're going to have 2 water molecules because each water molecule only has 2 hydrogens in it. And then when you look at that, 1 methane makes 1 carbon dioxide because that's the only source of carbon on each side. And when you add up all the oxygen on the product side, there are 2 in the carbon dioxide, 2 in 2 moles of water. And so we need to have 2 times O2, which is also 4, to give you the right number of oxygen. So now that reaction is balanced. So it's common practice to use the smallest possible whole number coefficients in a chemical reaction. So back here, we could have done a 1/2 mole of methane plus a mole of O2 and balanced it that way, but it's more standard practice to make sure everything's a whole number. So these coefficients represent the relative number of reactants and products, and they may be correctly interpreted as ratios. So in that previous example, methane and oxygen react to form carbon dioxide and water in a 1:2 to 1:2 ratio. So it takes 1 methane and 2 oxygens to make 1 carbon dioxide and 2 waters. So this is just showing that in a more visual way, looking at how that mixture has changed on the 2 sides of the equation. So on the left-hand side, we have methane and oxygen, and on the right-hand side, we have carbon dioxide and water. So this is just showing it as their structure. So when you balance a chemical equation, equal number of atoms for each element are represented on the reactant and product side. So I've already mentioned that we're not changing carbon into a different element. We're simply changing what carbon is interacting with. So on the left-hand side with hydrogen, on the right-hand side, oxygen. So it's balanced when you have equal carbon, oxygen, and hydrogen for this particular reaction. So the number of atoms for a given element is calculated by multiplying the coefficient of any formula containing that element by the element subscript in the formula. So we looked at, for example, methane on the left-hand side and said a molecule of methane has 1 carbon and 4 hydrogen atoms. Therefore, the number of hydrogen on the left-hand side in this equation is 4 hydrogens. And same thing over on the product side, all that hydrogen forms water. Each water molecule has 2. The subscript 2 says that each water molecule has 2 atoms of hydrogen, and we have 2 molecules of water. So 2 times 2 says we have 4 hydrogens, and that's why it's balanced on both sides. If an element appears in more than one formula on a given side of the equation, the number of atoms represented in each must be computed and then added together. We had to do that with the oxygen on the left-hand side. We had to say that both CO2 and water had oxygen to contribute. So we looked at this already. We've already talked about it. Each CO2 on the product side gives you 2 oxygen atoms per CO2 molecule, and each of those waters gives you 1 oxygen per 1 molecule of water. So you end up with 4 oxygen atoms on the product side. So So you just check. So we've gone through this. If you have a carbon on the reactant side, 1 times 1, we have 1 carbon in the methane. On the product side, 1 times 1, 1 carbon in 1 CO2 molecule. So you can look at this, stop if you want to look, but this is exactly the process that we just used. So if we have another unbalanced chemical reaction, can be balanced by a fairly simple approach, just by inspection. So when we look at it, we have water on the reactant side, hydrogen and oxygen on the product side. When we want to balance that, we have, let's see, we have hydrogen 1 times 2 because each water molecule has 2 hydrogens, gives you 2 hydrogen on the reactant side. On the product side, each hydrogen gives you 2. So the hydrogen is balanced, yes. But when we look at the oxygen, no. On the reactant side, we have 1 times 1. We have 1 oxygen atom in a water molecule, so we only have 1 oxygen. But on the product side, we have 1 times 2 because each oxygen is diatomic. It has 2 atoms of oxygen in it. So that's not balanced. We need to figure out a way to get the oxygen balanced. So to achieve the balance, the coefficients in the equation must be changed. Subscripts define the identity of the substance, so we can't change them. So when we look at how to balance this, we couldn't simply remove the 2. We couldn't make it O. We couldn't just make it single atoms of oxygen because that's a different molecule. It's an atom instead of a molecule. So in order to balance, if the oxygen isn't balanced, we need to add a coefficient to the left of that molecule. We need to say how much of the oxygen do we need. Oops. Okay, so if we change the amount of oxygen by making it 2 waters, then, so then that means 2 water on the left-hand side gives me 2 times 1, 2 times 1 oxygen in each of those. So now the oxygen is balanced, but we also will then need to put a 2 out front of the hydrogen on the product side, because on the reactant side, we now have 4 hydrogen atoms, and so we need those on the product side. So we had to put that coefficient out front of the hydrogen on the product side to now get both the oxygen and the hydrogen balanced. So sometimes it's convenient to start out by balancing with fractions. So in this case, where we have ethane also in the same reaction, this is a combustion reaction. So if you look at this reaction and compare it back to this one, this is the combustion reaction of methane. This is the combustion reaction of ethane. It's another component of fossil fuels. So in this, when you balance it, if you start out with C2H6, which is the ethane, you end up with 2 moles of CO2 because each ethane has 2 carbons in it, and each CO2 only has 1 carbon, so we need to make 2 moles of CO2. And to balance the hydrogen, we have 6 hydrogen on the reactant side. And if we put a 3 out front of the water, we'll have 6 hydrogen atoms on the product side. And that would leave us with 3 times 1 oxygen plus 2 times 2, 4 oxygen. So that would leave us with 7 oxygen atoms on the product side. So in order to get that with O2, you'd have to multiply the O2 by 7/2. So when you do that, then to come back to the convention, it's best then to multiply that whole equation by 2 to change those into whole numbers rather than fractions. If you multiply everything by 2, your ratio doesn't change, so you're good. Additional information that you should put in a chemical equation. The first is the physical state of reactants and products. So when we look at this reaction of sodium with water, it's a chunk of solid sodium metal. So we'll put solid, S in parentheses after the sodium, and we're going to drop it into liquid water. So it's at a temperature where water is a liquid. And we're going to make sodium hydroxide, and the AQ means it's going to be in a solution of water. Aqueous means a solution where the solvent is water. And the other product is hydrogen in the gaseous form, so that's going to leave the reaction mixture. Sometimes you put over the arrow. This is done more in organic chemistry than in Gen Chem, where if, for example, you need to heat a reaction in order for it to take place, if you put that little delta up above the arrow, that means you have to have the reactant and you have to give it some heat, some energy in the form of heat. That in this particular last equation, that 3 and that 2 should be subscripts. They must have overlooked that when they did it. So it'd be calcium carbonate is CaCO, 3 as a subscript, which means you have 3 oxygen atoms. And then same thing with CO2, which we've seen earlier. CO2 should be CO2 as a subscript. So now if we're talking about reactions, our equations for ionic reactions, so reactions that take place in a solution of water, where it's an aqueous solution. When ions are involved, the chemical equation can be written with various levels of detail. So this first one is a molecular, and the type of reaction that we're going to be looking at here is going to be called a precipitation reaction. So if it says you have calcium chloride and it's aqueous, that means the ions are pulled apart, and we'll see in a second that we could write an ionic form. But in the molecular form, you'll keep them together. And silver nitrate is aqueous. Calcium nitrate is aqueous. And then silver chloride becomes a solid. That's what's going to be what actually changed in this reaction. So molecular equations don't explicitly represent the ionic species that are present in solution. And in order to understand what that means, I think it's best to go on to writing a net ionic equation. So yes, so when ionic compounds dissolve in water, they can dissociate into their ions. So when you say calcium chloride in this reaction and you say it's aqueous, that means the ions have been pulled apart and you have Ca2 plus cations and Cl minus anions. And in order to get that balanced, you need 2 of those -1 anions. So when you break apart calcium chloride, you get Ca2 plus and 2 Cl minus anions. With the silver nitrate, same thing. If it says it's aqueous, we pull the silver apart. But notice here, nitrate would be in your polyatomic anion table, which I'd give you on a test, so that you'd realize you don't pull apart the N and the O, you only pull apart the cation from the anion. So we'd have Ag plus and NO3 minus. We have 2 of each of those because we saw, because back here we recognized that if this is going to be balanced, it takes 2 silver nitrates for every 1 calcium chloride. Okay, and then the last one is just showing you the same thing for the calcium nitrate, which is on the product side. So once again, the NO3 minus is a polyatomic anion called nitrate. You'd find that in a table. So you pull apart the calcium from that polyatomic anion. You don't then also pull apart the nitrogen and the oxygen. So in this case, because silver chloride is different in that it doesn't have aqueous after it, silver chloride, which I'll do a demo in class and we'll make some silver chloride, will remain a solid chunk. Water can't pull apart the silver and the chloride. So in that case, when it dissolves, it will not dissolve in water, and so we won't have any ionic forms for it. So when we write out the complete ionic equation, we started with the molecular equation where the ions were kept together. But now we know that the calcium 2 plus, the Cl minus, the Ag plus, the NO3 minus, all pull apart in water. And so now we have those individual ions. And on the product side, we have the individual ions for the calcium 2 plus and the nitrate. But the AgCl solid, we won't pull that apart. So for a complete net ionic equation, you pull apart the ions for things that do dissolve in water. And then to really look at this, it's kind of a mess. When you look at it, you really wonder what actually was the chemical reaction. So A net ionic equation shows you more explicitly what actually changed. So on both sides of our reaction, we have Ca2+ dissolved in water and NO3- dissolved in water. So they're floating around. And so they don't change from reactant to product side. So when we represent a net ionic equation, we're actually representing what changed. So if calcium and nitrate didn't change, we call those spectator ions. They're the same on both sides. You can cross them out. And what you'll see actually changed is that silver plus and CO- ran into each other when they were mixed, and water couldn't hold them apart, so they became a solid compound. So this is the net ionic equation that represents what truly happened in our chemical reaction, makes it much easier to look at it. Doesn't mean the calcium and the nitrate aren't there. They're still there, but they're not changing in the reaction, so we leave them off. So our next goal will be to learn about different types of reactions. So we want to be able to classify reactions as either precipitation, which this was a precipitation reaction, acid-base, and oxidation reduction. We want to be able to classify these three types given appropriate descriptions or chemical equations. So if someone describes to you or gives you an equation, we want to be able to look at that reaction and then be able to say it's one of these three types. We want to be able to identify some common acids and bases, predict the solubility of common compounds by using solubility rules. So for example, how would you have known that silver and chloride wouldn't stay separated in water, that water can't hold them apart? You'd use a solubility rule, which is just a set of rules that people went into the lab and figured out. They mixed ions and saw whether or not they would form solids or not. Compute the oxidation states for elements and compounds. So these are our goals as we look at classifying these types of reactions. So a precipitation reaction is one in which dissolved substances react to form one or more solid products. They're also known as double displacement, double replacement, or metathesis reactions. So we'll focus just on understanding the precipitation part. Many reactions of this type involve the exchange of ions between ionic compounds in aqueous solution, and precipitation reactions are common in nature and industry. They're often used as a way to measure how much of something is present. So if you had a water sample and it was contaminated, it was maybe mine drainage, it was contaminated with silver, and you wanted to know how much silver was in there, a common way to do that would be to add some chloride and then measure the mass. And in that process, you would figure out how much silver was present because all the silver would become silver chloride. So solubility is the maximum concentration of a substance that can be achieved under specific conditions. Substances that have a relatively large solubility are said to be soluble. So something like sodium chloride, the salt you put on your food, it's very soluble. So you can put a large quantity into your soup, for example, and it won't stay as rock salt. It will dissolve into sodium plus and CO- cations and anions. A substance will precipitate when a solution conditions are such that its concentration exceeds its solubility. So you can, with table salt, get to the point where you've put so much in that it won't dissolve anymore. It just takes an awful lot. And substances that have a relatively low solubility are said to be insoluble. So something like silver chloride, we say it's insoluble, and that when you mix these two, you'll get silver chloride solid, but it's actually very slightly soluble, and it's actually used in purifying like water for swimming pools and things often, because you put in a crystal of silver chloride and just a little bit will dissolve and you'll get enough silver in that water to kill bacteria, but you won't get enough silver in that water to impact human life or whatever is using the swimming pool. So this is a small solubility table that you'll always be given on a test. And notice as you read it on the left-hand side, on the top, it says these soluble compounds contain, and then there are exceptions to these rules. So number one, group 1 metal cations and the ammonium ion. Okay, so there are no exceptions to that one. Next, the halides tend to be soluble, except if you look on the exception side, on the right-hand side, the halides of silver plus, mercury 2 plus, and lead 2 plus. If you have a halide in solution and you add one of those cations, it would form a precipitate, because the right-hand side is saying these exceptions aren't soluble. Acetate, bicarbonate, nitrate, and chloride ions are soluble, and there are no exceptions on the right-hand side. The sulfate ion tends to be soluble, except if it sees silver plus, barium 2 plus, calcium 2 plus, mercury 2 plus, lead 2 plus, or strontium 2 plus. So if you have any of those ions in solution, it will precipitate with sulfate. And then when you get to the bottom of the table, they flip it. These compounds on the left tend to be insoluble: carbonates, chromate, phosphate, sulfide ions. The exceptions, and when those things would be soluble, is compounds of these ions with group 1 metals or ammonium ion. And then on the left-hand side, hydroxide tends to be insoluble. But if hydroxide sees a group 1 metal cation, so any of the group 1, or with barium 2 plus, it will be soluble. So think about the table, and we'll use it in a lot of examples in class. So here is just a molecular equation that shows you the reaction of potassium iodide with lead nitrate, and it makes lead iodide and potassium nitrate. And if you look at our solubility rules, let's go back and see, how did we decide that the lead iodide was not soluble? So we went back here and said iodide is a halide, so on the upper part of the left. But when it runs into Pb2 plus, it's not soluble. So PbI2, lead iodide, is not going to be soluble. And so we'll put an S after it when we write the molecular equation. And then when we write the net ionic, the only thing that's truly changing is the lead 2 plus, which is floating around on the reactant side. So you're mixing a solution of Ki with PbNO3 2. So potassium iodide's in one solution, lead nitrate's in another. You're pouring them together. And so when you pour them together, the lead 2 plus that was floating around in one of your tubes, it's going to now be introduced to the I minus that was floating around in the other one. And when they mix, water can't keep those two ions apart, and the precipitate will be lead iodide. This is just a picture of it. It's a pretty yellow compound, and it gives you that idea why you call it a precipitation reaction. It looks like it's snowing yellow snow in that picture. This is just another example. This one I will do in class. I like this example. So silver chloride plus sodium chloride plus silver nitrate. The silver, if you look back at your solubility table, is an exception to the halides being soluble. So when the Ag plus sees Cl minus, water can't keep them apart. And so you get AgCl solid, silver chloride solid. And if you write that as a net ionic, the sodium plus and the nitrate on the reactant side are in the same form on the product side, so we can leave those out. And the only thing that's truly changing in this precipitation reaction is Ag plus is running into Cl minus. And when that happens, water can't keep them apart. And so you're forming the precipitate silver chloride. So I think I'll take a break here. I'm not sure if I'm exactly halfway through, but it seems like it's a good place to take a break.